or not classwork, your homework first. All right, you had on page number 75, you had questions 1 and 2 for that section. Let me get over there. All right, what is diffusion? All right, diffusion is the process of mixing molecules of one substance to another by random molecular motion. Number 2, state Dalton's law of partial pressure. All right, Dalton's law says the total pressure of a mixture of gases is the sum of all the partial pressures of that gas. So each of the little pressures all added up all together equals the total pressure of your entire container. All right, then on page 76, you had problem number 3. All right, so problem number 3 for that one. A tank of helium at 25 degrees Celsius had a pressure of 100 atm and a volume of 50 liters. How many 10-liter helium balloons can be filled with such a tank, assuming no change in temperature and the pressure in the balloons of 1.05 atms? All right, so thinking about this one, I'm just going to write over here because I have classwork over there, so we'll talk about that in a second. All right, so I'm looking at this and it tells me I have a temperature, I have pressure, and I have volume. So what's the equation we use whenever you're talking about temperature, pressure, and volume? Combined gas law. So P1 times P1 over T1 equals P2 times V2 over T2. All right, let me plug in my variables so that way I'll know what I'm starting off with. That'll help me to see, okay, what am I doing? What do I start with? All right, so it says I have 25 degrees Celsius. Now, can I use Celsius ever? No. So I have to go ahead and add it to 273.15. So for this one, so 273 plus 25, that's, oh, I forgot to do fast math for this one. Let me get my calculator. I haven't had my coffee yet. Till I have my coffee, I don't trust my math skills. So plus 25. This is why you're allowed to have a calculator in this class. 298.15. Alright, so that's my first temperature. It has a pressure of 100 atm. So 100 atm. Probably should have left more room, but that's okay. So 3 sig figs because of the decimal point. Alright, and a volume of 50 liters. Alright. So it says how many 10-liter helium balloons can be filled in the tank. We'll come back to that. Assuming no change in temperature. Oh, temperature doesn't change. Alright, so if temperature is the same on either side, then do I have to factor it into my equation? No. Now, you might have noticed, well, why'd you write it down then to begin with if you know it doesn't change? Well, that's part of the reason why. If you notice, oh, okay, if it's the same on either side, I can just cancel them out. So I don't have to worry about it. So that's the reason why you want to write it out to help you to see, oh, okay, this helps me figure out from my combined gas law what I'm actually doing. Alright, but it says no change in temperature and a pressure of 1.05 atm. So 1.05 atm. So it's asking number of balloons, but keep in mind it says 10 liters. So if it's 10 liters, what property am I finding? Volume. So I'm finding this one. So if the bottom part doesn't cancel out, what law are we working with? We're talking about pressure and volume. Boyle's law. So good job. So for this one, if pressure is increased, we should expect volume to decrease. So let's go ahead and let's solve this. So plug it into my equation. So 100, I'm going to leave off units so it'll fit better, times 50, that's not 50, 50, the temperature doesn't matter, so I'm going to leave that off, equals 1.05. I'm finding V2. Alright, how do I get V2 by itself? You can still see it as long as you don't see me. Right? I divide by the 1.05. That'll cancel it out. Alright, so this problem turns into 100 times 50 divided by 1.05. You get 4,761 liters is what this boils down to. Keep in mind, that's not the answer, because it's not asking you just what's the second volume. It's asking you how many balloons could I fill. Well, each balloon has a volume of 10 liters. So divide 10 into 4,761, and that'll tell you how many balloons you can get from it. From this one, you're going to get 476.1, but it's asking you how many balloons. This isn't a full balloon, you can just ignore it. So it's 476 balloons. That's your total answer. So 476 balloons. That's the answer for that problem. Alright, now let's look at your classwork. This will help you kind of to think back through it and help get your mind going for it. So I want you to do on page 71, application number 3. And then on page 76, problem number 4. Again, just giving you a little bit more practice and trying to hopefully wake you up this morning or this afternoon or wherever it is you're doing this. So I hope you start thinking about chemistry again. So go ahead and pause the video. That way you can go ahead and work these two problems out. It should only take you about 5 to 10 minutes. So if you're getting really stuck and just sitting there and don't know what to do, alright, then go ahead and unpause the video and come back. But you want to try to figure it out as best you can. So try to spend about 5 to 10 minutes trying to figure it out. Alright. Okay, well, assuming that you've worked it and that you come back now, we're going to go ahead and talk about that page 71 application number 3. Alright, so the absolute temperature of the inside of the tank of compressed air is doubled. Use the combined law to predict what will happen to the pressure inside the tank if the volume remains constant. So this one's not an actual math problem. This one's just asking you just to think about it. So let's talk through this one. The absolute temperature of the absolute temperature inside of a tank of compressed air is doubled. So that means that the temperature is doubling or going up. Alright, use the combined gas law to predict what will happen to the pressure inside the tank if the volume remains constant. Alright, so the volume doesn't change, so you don't have to worry about it. But if the temperature goes up, what should happen to the pressure if the volume stays the same? Right, pressure should also go up. Your book's trying to make you think through that, okay, that if volume and temperature are directly proportional to where if one goes up, the other one goes up. As a side note, if volume can't change, because the balloon wants to spread out as much as possible, or the hot air balloon, or wherever, or for this one, the compressed tank, that this one, compressed air on the inside of the tank, it wants to spread out, but the volume is locked in, so the pressure is building on the inside. So, your book's making you think that, okay, if the temperature doubles because the volume wants to double but can't, the pressure will double as well for it. So, if you remember that from physical science, that's technically a Montan's law. Your book does not talk about him at all this year, so that's okay, you don't have to know him. But that's just what it's getting you to think of, that okay, that pressure and volume, both of those are directly proportional to temperature. If temperature increases, either the volume will increase, or if the volume can't, then temperature will increase, and then vice versa. Alright, so looking now at number 4 on page 76, problem number 4, hopefully just getting you awake and going this morning. Alright, a gas occupies 24.5 liters at 38 degrees Celsius and is cooled to negative 8 degrees Celsius at a constant pressure. What will the final volume of the gas be? Alright, so hopefully you recognize, okay, I have constant pressure, I have changing volume and changing temperature. So looking at our combined gas law, this is our kind of shortcut one, you want to figure out, okay, which things don't matter, so that way I can solve this problem. Alright, so again, get back into it. So a gas occupies at 24.5 liters at 38 degrees Celsius and is cooled to a new temperature, and then you're asked to find the new volume. So it says it's at a constant pressure. So the constant pressure, or the pressure, is not changing. So if the pressure is not changing, what law am I working with where it says if the temperature changes, then the volume must also change? Charles' law. Perfect. Alright, so let me write down what am I starting off with. So the first volume, I erased my chart by accident. I'll re-add it later if I need to. The first volume is 24.5 liters. My second volume is what I'm trying to find. So that first temperature, it gives it to me at 30 degrees Celsius. Remember, you can't use Celsius though. So this one turns into 311.15, while the negative 8 is 200, and nope, 265.15. So that's the second temperature. So make sure I copy them down correctly. Yep. Alright, so how do I set this up? So remember, we're ignoring the P1 and the P2. So first volume, 24.5 over 311.15, 265, and that's right. It's the second volume. Alright, so how do I get the V2 by itself? Right, I have to multiply or move it, so 265.15, set it off to the side. So I multiply 265.15 times 24.5, then I divide by 311.15, that gives me 20.877, and then it just keeps going. Alright, so for this, I want to round to proper sig figs. This one has 5, this one has 5, this one has 3. So I have to round this 1, 2, 3 sig figs. That's a 2, just looks funky. Alright, so rounding this to 2 sig figs turns into 20.9. Since this one is liters, that means there has to be liters as well. So that's the answer to that problem, just kind of getting you awake and thinking about it. Alright, so hopefully this is good practice for you, figuring out how do we use the combined gas law. So we're going to go through some of your terms and definitions. I haven't made you copy class terms definitions like I have in U.S. history yet, just because you need to know the math, you need to know the terms and definitions as well. Tomorrow's Friday, so make sure you are ready, just in case. Alright, so take out a piece of paper so you can write down these terms and definitions you don't know as we're going through these. So if you can't think of them or say them before I do, you want to write them down so that way you can study them later. Alright, so what do you call the property of gases to be mixed? So there's a term that means that they can be mixed together. Miscible. What do you call it whenever they mix or whenever they're moving across the room? What do we call that? You learned a better version of this, a better definition of this today. Hopefully we'll learn and talk about it if we have time. Diffuse or diffusion. Alright, what are the 5 parts of the kinetic theory of matter? Name as many as you can. If you can't name any, then you're in trouble. You need to make sure that you know them. Alright, so the first one is that the gas molecules are in constant motion. The gas molecules undergo elastic collisions. The gas molecules, their energy is related to temperature. They have very negligible, it doesn't really matter, volume to the volume of the gas as a whole, and they have very negligible attraction to each other. What do you call a gas that exactly obeys the assumption of the kinetic theory? An ideal gas. Good. Alright, what is the equation for kinetic energy? I just got out that piece of chalk. Oh well. Alright, what is the equation for kinetic energy? So K E equals 1/2 mv squared. So hopefully you recognize that. Alright, what's the equation for pressure? P equals force over area. So if we recognize that one, go ahead and adjust this back. I think that bar is crooked. I'll have to fix that later. Yeah, you can still see everything. Alright, what is the... It's not lined up anymore, so it's going to bother me. What is the SI unit for pressure? Pascal. Alright, who discovered atmospheric pressure? That air has weight. Torricelli. So just make a note for his first name, Evangelista Torricelli. So make a note for him. What is the device that's used to measure air pressure? Barometer. What is one that what do we call the one that has the flexible sides to where it can flex in or flex out and it doesn't have mercury? Aneroid barometer. Good job. Alright, if I have, let's say, 20, I did 20 yesterday. If I have, we'll say 1,208 torr, how many millimeters of mercury do I have? We got 1,208, whoops, millimeters of mercury. How many atmospheres do I have, or ATMs? Technically it's just ATM, we don't say ATMs. Habit. Alright, well, we're going to say, if we're, now for this, we're not going to worry about sig figs since we're just figuring this out. But for this one, if I have 1,208 millimeters of mercury, I have 1.589, we'll just leave it before sig figs since these have 4 sig figs. ATM. So make sure that you understand that, okay, that these two are equal, but I gotta divide by 760 if I'm going from millimeters of mercury or torr into ATM. So that's where I got this number from. So these two numbers equal each other, but you have to divide by 760 if you want to figure out if you're going from torrs to ATM, or torr or millimeters of mercury to ATM. And then vice versa, you want to multiply if you want to go from ATM to torr or millimeters of mercury. So make sure that you understand what you're doing to that. We've been talking about that for a couple of days. Alright, you're talking, what is the device that's used to measure the pressure of a gas sample? Manometer, good job. So if I have a manometer that's open to the atmosphere, and the mercury on the inside has shifted towards the atmosphere, which one's stronger? The gas. So do I add to the atmospheric pressure, or do I subtract how much it's moved from the atmospheric pressure? I add it because it's stronger than the atmosphere, so however much it moves by, I need to add it to what the atmosphere already is. What if it shifts towards the gas side? Which one's stronger? The atmospheric pressure. And then what do I do with how much it shifted? Do I add it, or do I subtract it to how strong the atmosphere is? Subtract it. So that way it'll tell me the atmospheric pressure is stronger, so the pressure of the gas must be weaker, so I subtract how much it's moved by. What if it's a closed manometer and I have it shift on the inside? Do I care what the atmospheric pressure is? Nope, because it's closed. So however much it shifts by is the total pressure of the gas. Alright, talk about the gas laws. What gas law says that temperature and temperature and volume are directly proportional? Which law? Charles' law. So I didn't ask them in order, so just make sure that you know Charles' law, volume and temperature are directly proportional. What law says that volume and pressure are inversely proportional? That's Boyle's law. Good job. What temperature scale do you have to use with gases? You have to use the Kelvin scale. And theoretically, what should happen at 0 degrees Celsius? Sorry, 0 degrees Kelvin, absolute zero. The volume should also be 0 liters, so you should theoretically shrink down to nothingness, but in real life we don't see it do that. Alright, what is the combined gas law? Combined gas law, what's that equation? Good, make sure that you note it and that you've learned it. Alright, what is the temperature at STP? So standard temperature and pressure, what is the temperature at STP? 0 degrees Celsius, or 273.15. What's the standard pressure at STP? 1 ATM. So just make sure that you note all those things. Alright, so we left off on page 69. We spent yesterday mainly going over all the maps, so today I have to talk kind of quick to make sure that we get through all of our material. Alright, so several other laws that you have to know. Alright, Gay-Lussac's law. So make it of him, so Joseph Gay-Lussac, that he was working with the volumes of gases, and he noticed several trends. So he didn't work with the equations, or he didn't figure out exactly what was going on, but he noticed, this is kind of like a weird idea, where he would notice if I would have 3 volumes, so it could be milliliters, it could be liters, but he would say, if I have 3 volumes of hydrogen, if I combine it to 1 volume of nitrogen, I get 2 volumes of ammonia. So it's 3 to 1 to 2. Alright, well if I'm working, let's say, with 1 volume of nitrogen, and I combine it with 1 volume of oxygen, then I'll get 2 volumes of nitrogen monoxide. So it's a 1 to 1 to 2 ratio. And then the last one, 2 volumes coupled at the bottom of carbon monoxide, 1 volume of oxygen, I'll get 2 volumes of carbon dioxide. Now as you work with these, you notice, okay, I have these ratios of small whole numbers over and over and over again. Now we would write these out as balanced equations instead of just saying volume. So if it makes you feel better to write them out. So 3, I don't know if that's going to be large enough to show up. So I'm going to write it over here. So, well, I'll just write big. So we would say 3 H2 plus HN equals NH3. Hopefully you recognize what ammonia is as a side note. Oh, if I legitimately ripped my tube. Almost. So this is the balanced equation for what he's talking about. Remember, hydrogen, it's dihydrogen and dinitrogen, so that's why it has to be balanced. But he would notice, okay, that it's for the balanced equation, it would be 3 molecules of dihydrogen with 1 molecule of dinitrogen will equal 2 molecules of ammonia. You could do that for all of these. I'm not going to take time to write out all the balance equations, but he was just noticing it's that ratio. We would say it like a mole ratio, so 3 to 1 to 2, but he was working with volumes of gases. He was noticing, if I have it where there's 3 liters of hydrogen and I combine it with 1 liter of nitrogen, I get 2 liters of ammonia. Or if I do 3 milliliters of hydrogen and I combine it to 1 milliliter of nitrogen, then I get 2 milliliters of ammonia. He was noticing it's that trend of its small whole numbers, that it's these ratios of 3 to 1 to 2. So that's what he was noticing, that whenever you combine these volumes together, they combine in a set of small whole numbers. So that's what he's talking about. So Gay-Lussac's law of combining volumes. When measured at the same temperature and pressure, the ratios of the volumes of gases that react or that are formed are products of small whole numbers. And that makes sense because whenever we see a balanced equation, we're working with small whole numbers as well. So speaking of those, so Gay-Lussac's law of combining volumes, when measured at the same temperature and pressure, the ratios of the volumes of the gases react or that are formed as products of small whole numbers. Just make a note of that he was looking at the ratios of the gases. As long as they're kept at constant temperature and pressure, they would combine in these small whole numbers. Alright, so that's Gay-Lussac's law. Avogadro's law, so this is counts Amedio is how you say it, Avogadro. Now remember, this is what Avogadro's number is named after. He did not actually come up with Avogadro's number, but he came up with this law, and that's probably the reason why we named Avogadro's number after him, was because he did the starting ideas. Alright, now remember, what's Avogadro's number? 6.022 times 10 to the 23rd, so make sure that you know it. Alright, what he was doing was he was noticing with the number and with the volume of the gases. So, Avogadro's law says that the equal volumes of gases at the same temperature and pressure, that they contain equal number of molecules. So he was noticing, okay, if I have a substance of equal temperature, that if I have the same temperature and pressure, that it's going to take up the same amount of volume or space. That's because, remember, the molecules want to spread out on the inside as much as possible. And so because of that, he would notice, okay, if I keep it at a constant pressure and a constant temperature, then they will have the same volume. So, speaking of that, so equal volumes of gases, the same temperature and pressure, contain the equal number of molecules. So we said, okay, now some molecules might be larger, like methane, it's CH4. So for this one, if I'm going to have it at this pressure and at this temperature and at this volume, it has to have have the equal number of molecules on the same side for it to be this constant pressure and volume and temperature, so for them to, so that way they don't have an extra number of molecules. Your book points out that this one only works out for ideal gases. And your book points out the kinetic theory of matter. This is the reason why it works this way. That at a given temperature, the average kinetic energy of any gas molecules will be the same regardless of its size, because temperature is directly proportional to kinetic energy. So if I keep them all at, say, it doesn't say at this temperature, but we'll say 25 degrees Celsius. And that means that they should all have the same kinetic energy. Since the pressure of the gas is a little collision of the gas molecules, the greater number of molecules indicates a greater pressure. So since they have the same kinetic energy, since they're all at the same temperature, that means they all want to spread out the same amount. So the pressure should be the same for them as well. Your book points out that any pressure differences must be due to the different number of molecules. If I were to add more inside of it, it would have a higher pressure because there's more molecules moving around. So even though these molecules are larger, if I keep them at the same temperature and pressure and at the same volumes where they are stuck in the same container, the number of molecules on the inside will be the same. So that's what it's talking about, that any pressure differences must be the different number of molecules of equal pressures as well as the equal volumes of it at the same temperature. That must mean they all have the equal number. Now some of them are larger, but we're talking about the number of molecules. So that's what it's talking about, that if I keep it at a constant temperature, at a constant pressure, then a constant volume from one gas to the next, it must be because they have those equal number of molecules on the inside. So your book points out you can state this mathematically by saying volume is proportional to the number of molecules, instantial number of molecules in this case, Or you could put it, it probably tells you that N is the number of molecules. You could also relate it to the Kn with the P and T or constant. But basically what it's saying that, okay, if I want to increase the volume, I have to increase the number of molecules if pressure and temperature are all the same. So if I want to increase the volume, then I need to increase the number of molecules if I keep pressure and temperature the same. So they're working with number of molecules, figuring out how many are on the inside, and that's where we get Avogadro's number from. That if I have 1 mole of a substance, I have the 6.022 times 10 to the 23rd. Because if it's work with the number of molecules and gases, that's why the number is named after him. Alright, so moving on then to molar volume. Now, do you make a note of molar volume? You want to memorize this number. The volume per mole of a gas under specified conditions is the molar volume. Since we're working with STP, that's our standard temperature and pressure. If we have a standard temperature and pressure, then we can say, okay, at this temperature and at this pressure, if we have these number of moles, so if I have 1 mole, I should be able to have a certain volume. So going kind of backwards with Avogadro's law, if I have a temperature and a pressure, I have the number of moles, and the last variable is volume. So that's what it's talking about with molar volume. For gases that behave very close to ideal, the molar volume at STP is 22.4 liters per mole. So make a note for that one. This one relates us to gas volume and moles of the gas. This one only applies to gas though at STP. So if it's not at STP, if it's not at 0 degrees Celsius, and if it's not at 1 atm, this liters per mole will change. So those are the 4 variables we're working with Avogadro's law. You don't get a full-on equation, you get the ideal gas law from this. But just make a note though that he says, okay, if I have constant temperature and pressure and volume, then I know that I have an equal number of moles on the inside. So going from that, if I know temperature and pressure, so standard temperature, 0 degrees Celsius or 273.15 Kelvin, pressure, 1 atm, then if I know I have 1 mole of gas on the inside, then I know how much volume it'll take up. So you want to memorize this value. You need to memorize. So 22.4 liters per mole. So make a note for that. Mark that one. You want to know it. Make in mind this doesn't work though for solids or liquids. This only works for gases. Alright, the ideal gas law. Now we can use this if we're going to talk about numbers of moles, we're going to talk about volume, temperature, and pressure. We can use this to get the ideal gas law. So I'm going to write this off to the side. So it's pressure times volume. N stands for number of moles. R is a constant. We'll talk about R in a second. And the last one is temperature. This is the ideal gas law. So it's pressure times volume will equal the number of moles times a constant times temperature. We'll talk about it again in a second. So there are several things that scientists have discovered with Avogadro's law, Boyle's law, and Charles' law. They notice, okay, volume is inversely proportional to pressure. That volume and temperature are directly proportional, and then volume and number of moles are directly proportional. So because of that, they could rearrange this to figure out any one of those 3 as long as they know that constant. So the R in this equation, you'll want to note what the R is. So whenever you're taking this amount and plugging it in, that's what they were using to figure out what R is. So your book points out in real life, not every gas behaves exactly perfectly, but it works out reasonably well. So in order to find out what the R is, they knew, okay, if I know what the pressure is, if I know what the volume is, if I know what the number of moles are, if I know what the temperature is, I can find R as a constant. So for this one, that's what they were working with. So if you're talking about an STP, what's the temperature then? 273.15. The number of moles, so if it's at STP and it's 22.4 liters per mole, how many moles do I have? 1, so 1 mole. Volume, 22.4. I did not leave enough space. I always do this. And then at STP, what's the pressure? 1 atm. So, reshifting this around to get R by itself, your book gives you the equation on the bottom of page 70, so rather than trying to reshift it around, I'll just use theirs. So it's 1 atm times 24 divided by the 273 and the 1. That gives us 0.0821, and then it's all of the units, so you need to note the units. So it's liters times atm divided by Kelvin per mole. So you want to note the full equation for it. This is where we get our R constant from. You don't have to note necessarily the reason why, but we use this equation and R always represents this. I think I left out the decimal point. Yep. So whenever you're working with these equations with the ideal gas law, you're going to have to memorize what R stands for. Because since R is a constant, we don't have to refine it over and over and over and over and over again. So typically you might be asked to find out what's the pressure, what's the volume, or what's the number of moles, or what's the temperature. So since this is a constant, you don't have to find this. So you want to memorize this one, including its units. Now if these are the units for our constant of the ideal gas law, that means your volume has to be in liters, your pressure has to be in ATM, your temperature has to be in Kelvin, and it has to be moles for moles. So that makes sense though. So it has to have these units. So if you're given milliliters, you got to convert. If you're given torrs or millimeters of mercury, you got to convert. So that's part of the reason why you have to know these units with it. So it'll help you to determine, okay, what conversions do I have to do to figure this out properly. All right, let's practice with this. All right, I'm going to write R up here so I won't forget. R equals 0.0821 liters times ATM over K per mole. So that way we won't forget. But make sure that you memorize that value. Alright, so let's do that first practice problem. So on page 70, it gives you this sample or this practice problem. So let's go through that one. Alright, what pressure will 0.025 moles of dioxygen exert in a 400 milliliter flask at 25 degrees Celsius? Alright, so what are we finding? Pressure. This is what we're finding. So asking what pressure will 0.25 moles, so number of moles, 0.025 moles. Still did not leave myself enough space. R is still up there, so I'm just going to leave it up there, but this is still R. Temperature, 25 degrees Celsius. Alright, can I use 25 degrees Celsius? Nope, gotta be in Kelvin. So 25 plus 273.15, 298. 0.15 Kelvin. So that's temperature. And then volume, let's see, 400 milliliters. If it's 400 milliliters, can I use that? Nope, gotta be in liters. So milliliters to liters, this becomes 0.4 liters. Alright, so plugging all of this in, I have to get P by itself. So how do I get P by itself? Right, I just divide by the V. So plugging everything in over here, so P times the volume 0.4 liters equals 0.025. I'm going to have to write the R above it, 0.0821. I'm going to leave up the units over here so that way it'll fit. 0.02, nope, that's not the temperature, 298.15. Alright, so instead of multiply, divide down here, so 0.4 as well. Now cancel it out. So to solve this, it's 0.025 times 0.0821 divided by 298.15 divided by 0.4, and that'll give you the answer of approximately, again with the sig figs, your book just goes ahead and rounds it for you, but it gives it as 1.5. I want to see what the full answer is for that. Let me type it in really quick because the book doesn't give it to you. So 0.025 times 0.0821 times 209. Oops, I put this down here and it's supposed to be multiplied. I am so sorry. So if you were really confused by that, I am sorry. I put temperature in the wrong spot. Temperature is multiplied in this equation. This is why you should always leave room. 298.15. So it's these three numbers multiplied together because these three numbers are all together. And it's divided by the liters of the volume since we moved it over there. This is why you leave space, and I run into trouble when I don't leave space. So make sure whenever you set up your equations, you leave yourself plenty of room on your paper. Because that's where I run into trouble whenever I don't leave up enough room. Alright, so multiply those two together, divided by 0.4. Let me finish typing this in really quick. You can still see me. Times 29.8.15 divided by 1.5. I messed up. Yeah, 0.025 times 0.0821 times 298.15 divided by 0.4. Okay. So the answer in the calculator is 1.5298, and then it stops. Alright, so for number of sig figs, since we converted for this one, you don't want to worry about the 0.4. So you want to look at what you're starting off with. So 0.025, that's 2 sig figs. 400 with a decimal point, that's 3 sig figs. 25.0, that's 3 sig figs. But remember, since we're multiplying and dividing, we go off number, so my answer has to have 2 sig figs. That's why this gets changed into 1.5. Now we're finding pressure, so what unit do I use? Now keep in mind, it's not giving me a unit for pressure, so which one do I use? Can I just pick one? Nope, because remember, for R, it's liters per ATM, so this one has to be ATM. So that's why you want to memorize these units, because it'll tell you what units that your answers have to be in. Alright. I gotta stop remembering to talk up there. There goes both pieces, that's so sad. Alright, really quick. Alright, Graham's law of diffusion, talking about this one really fast for it. So, your book points out, if you were to spray a can of Lysol, or if your mom lights a candle, you'll notice the scent starts to spread throughout the room. He was noting, okay, that some molecules, they move faster than other molecules. That makes sense because some molecules are smaller than other molecules. And so because of that, since they're a smaller size, but they still have the same amount of energy, they can move faster. So the process of mixing molecules of one substance to another by random molecular motion is diffusion. This is why you have gases they want to mix together or try to spread off each other as much as possible. That's why you don't have, whenever you light a candle, the scent doesn't just hang out right above the candle. Now it's strongest there, it'll gradually diffuse throughout the whole room. So Thomas Graham, make a note for him that he noticed that the lightweight gases diffuse more rapidly than the heavier gases. Kind of like if you want to think of if you were to take a ping pong ball and then throw it with the same amount of energy that you use to roll a bowling ball, the ping pong ball will move farther or go faster because it has more energy in proportion to its size. So that's what it's talking about. The lighter molecules diffuse more rapidly because they're moving faster at any given temperature than the heavier molecules. So because they are lighter, and even though they have the same kinetic energy, because they're smaller, they're moving quicker. So that's where I came up with the idea of Graham's law of diffusion. You do not have to know the equations, but basically what it says: if I have a lighter molecule, it'll diffuse faster than a heavier molecule. So make a note, this principle that the diffusion rate of any gas is inversely proportional to the square root of the gas's molar mass. Basically, if it's heavier, it's gonna move slower. That's what it's talking about. So if it's lighter, it'll move faster. Alright, so make that. So lighter molecules, they diffuse more rapidly at any given temperature because they have more energy in proportion to their size. Alright, we'll go ahead and we'll stop there. I think that'll give you enough. I want to make sure you have time because of the classwork. Alright, so for your homework tonight, I wasn't able to run through a practice problem with the ideal gas law besides just this one. So I'm going to give you homework. Try to do it as best you can, but we'll explain it and we'll practice more tomorrow. So on page 71, you're going to do application number 4. So finishing up that section on page 71, application number 4 is over the ideal gas law. So use your equation, plug in your variables for it, and we'll talk about it tomorrow. Then you're also going to answer on page 75, question number 3, the concept review question number 3. And then you also want to do, alright, application number 1 on page 75. So you're doing on page 71, application number 4. You're doing on page 75, concept review number 3. And then you're using application number 1 on page 75. You don't have any reading because if you notice, you kind of finished up the chapter, so we're almost done with all of our material. So tomorrow will be the last day of new material. Then we'll start reviewing Monday and Tuesday for your exam on Wednesday. So be sure to email me if you have any trouble or if you're running into problems, for email and ask me. Alright, but this will wrap it up for tomorrow. So again, one more time. So it's application number 4 on page 71. On page 75 is concept review number 3, and application number 1 on page 75 as well. Alright, thank you.